Okay, today we're going to be doing a little bit of conversation about atomic structure, but I really wanted to make sure that we addressed our prefixes. Now, I want to remind you that these are the 8 prefixes that that for this class I would like you to know and memorize. So you should be able to know what the Greek prefix is. So giga, you should know what its abbreviation is and what its meaning is. So that way, if I give you 3,000 gigajoules, we should be able to break that apart. We should know that this G stands for 10 to the 9. That's 3,000 times 10 to the 9. And then we would have our base unit, which would be joules. That also means that if I were to give you something that's in kilograms, we should be able to change that to grams or even milligrams without needing any other conversion help, right? So these are important ones. They show up often, which is why I'm having you guys learn about them. And so we just want to make sure that we are prepared, okay? Now, from here, we're going to start into our new material. And so one of the things that we talked about is this concept of law of constant composition. So we're going to elaborate a little bit on this. Now, we talked about this in chapter 1 when we were talking about not elemental substances, pure substances. Right? Pure substances show up in the form of compounds. And so what's unique about compounds is that they have a definite composition. Right? It means that it's defined. They will always have the same relative number of atoms of each element for that sample. Right? Now, if that sample is made here or if it's made around the world, it still will have that same relative number of atoms of each element. And so this was first discovered by Joseph Proust, and it's one of the bases of the atomic theory, or Dalton's atomic theory, that we're going to build from. So it's this concept that things have the same ratio of their elements if they are the same material. Which seems really straightforward, but at some point, someone had to prove that. Someone had to prove that all water, no matter how it was made or where it was formed, would have the same ratio of 2 hydrogens for 1 oxygen. Whether you had a small, tiny drop of it, or if you had a big gallon, it would always be in that same ratio. The second concept is the law of conservation of mass. Now, in chemical reactions, we're not going to change that mass into energy. Now, that might happen in different types of reactions, but the law of conservation of mass is saying that the total mass of the substances at the end is the same as whatever was there before our chemical reaction took place. So all of our reactants, their mass must be equal to that of our product's mass. Now, if that's not the case, then it means that either we've lost mass somewhere along the way. So sometimes that happens when you're doing your chemical reaction, and maybe you transfer it from one beaker to another, and you might have lost some mass that way. A second could be that maybe we made a product that we didn't capture in our final weights. So that would be something like if we made a gas, maybe that gas has escaped, and so we're losing that mass. So this concept was first discovered by Antoine Lavoisier, and it's one of our other bases of the atomic theory. And so this is a really strong and important concept that we're going to see a lot in how we do our calculations. So when we do things like calculating what we think we should produce, our theoretical yield, or when we calculate how much material we should need if we want to make that much product, it's all coming back to this idea that whatever reactants we put in, their mass is going to be there in the products that we make. The other part is the law of multiple proportions. And so if 2 elements A and B form more than 1 compound, the masses of B that combine with a given mass of A are in the ratio of small whole numbers. So it's this idea that because we're dealing with these atoms, and our atoms are going to be our smallest parts, that we should have a ratio somewhere in there of these small amount of whole numbers to compare them against. Now, while we can make more than one kind of compound using the same two elements, they can't have the same relative number. So it's this idea that we really don't want to count compounds that are A, B, and A2, B2 because they're the same relative number of atoms compared to each other. Now, some of these laws get stretched a little bit as we've gotten a better understanding of it. But for now in our class at this beginning part, we're going to be looking for things like this. We're going to be looking for things like these. Later on, as you go higher up in chemistry, you might start to see things where they're written like this. Or we might have two options of things. But we're going to worry about that when we kind of get there. So for now, we're just going with this concept that while we can have two elements making new compounds, they are going to make some ratio of them, and new compounds will have different ratios. So that's the law of multiple proportions. So all of this is getting put together for our first atomic theory, which is Dalton's atomic theory, which is kind of impressive because this was made back in like the 18th century, right? And so this is a big step, because at that time, this is almost 200 years ago, there was a lot of things that they didn't know, or things that we take for granted that you should already know. This was when they were first starting out. So we know that elements are kind of the simplest of all of our substances. And we know that the smallest amount of an element is an atom. And so Dalton kind of took those two things, combined them with the law of conservation of mass and the law of constant composition, and he came up with these 5 basic principles. Now, this is a really good starting model of chemistry. Over time, our understanding of chemistry has evolved beyond this, and so all of these things are kind of not 100% true anymore. They've been stretched, but it is a good starting point. So we're going to start with this model, even though we might make it more advanced over time, just because it's a good and easy way to begin. So our first part is that all matter is made up of atoms, and those atoms are going to be these small, indivisible, indestructible fundamental particles. Now, we know since then that you can kind of break up an atom, but Dalton's theory at that time was that you had these really small atoms that everything was made up of. And so that is still true. We can see that when we look at our materials, we can take them and we can see that what's holding them together is these collection of atoms. And our technology has actually gotten so good that this is sheets of graphite, kind of like what's in your pencil. And we can now use what we call a scanning tunneling microscope. And we can visualize those particles, and you can see how they kind of look. That we have that same ring structure, that same shape, which would be the same as our atoms being connected there. Now, part number 2, atoms can't be created nor destroyed. Now, this is really similar to that law of conservation of mass. So it's this idea that all of those atoms that we start off with, they're going to be there at the end. This is a really big fundamental concept of how we balance our chemical reactions. Everything needs to be accounted for. When we write out our chemical reactions and we get to balancing there, everything that's going to be on the left side of the arrow is also going to show up on the right. If they're not equal, then it means we're either missing a compound or a chemical, or it means that our ratio of our molecules are off and we have to balance them. So all of our atoms, they're going to show up on both sides. We're not going to lose any of them. The other part, which we probably would assume is pretty straightforward, but at that time, they kind of had to lay it down as a foundation, was that atoms of a particular element are alike. So that means that they have the same size, the same mass, and the same properties. And it didn't matter where we got them from. So lithium that's here, or lithium that's in China, or lithium that's in Australia, they all have those same properties for their atoms. And so that's how we can kind of make them uniform. So even without trying and experimenting on those same elements all over the world, at that time they were trying to make this foundational concept that if it was the same, it would be that same element. If they didn't have the same size, the same mass, then they must be a different element or something else that was unique about them. That goes hand in hand with this idea that atoms of different elements are different from one another. So we should be able to tell using some type of physical property or some type of method that one atom of one element is different than one atom of a different element. There has to be something to stand them apart. They could be very similar. Maybe they have a very similar size. They might be very similar in their mass, or they might have very similar properties, but one of those has to be unique. They can't just all be the same. And then from there, a chemical reaction, it basically involves the union or separation of those individual atoms. So it involves us putting them together or taking them apart. So it could be us making water. We could take those two hydrogen atoms that we had before. We could have our oxygen atom here, and we could combine them to make a water molecule. And that counts as a chemical reaction because we're uniting that hydrogen atoms with the oxygen. We're also separating apart these two hydrogen atoms from each other. This is another diagram of a chemical reaction. This is what we call combustion. So this is methane, which is also known as natural gas. And from there, we're going to react it with two molecules of oxygen gas, and we're going to make carbon dioxide and two water molecules. You can see here how we've now broken apart the different molecules, and we've now created new connections. These oxygens are no longer attached to each other. They get split up. One goes to one side of the carbon, one to the other. These other two oxygens, they get split up and actually become two separate molecules. Our methane gets divided into two water molecules, and also the carbon becomes the center of our carbon dioxide. So chemical reactions involve that change. Those chemical bonds need to be broken and formed in order for it to count. If we don't break any of those bonds or form any of those bonds, then we don't have a chemical reaction. We would just only have a physical change. And so that's kind of the difference. And so those are the 5 basic fundamental principles of Dalton's atomic theory. And from there, we've kind of built on top of that. So one of the things that we're going to talk about is we're going to talk about the different particles that we eventually discovered that were smaller than the atom. Now, what I want you to do is I want you to write down this chart. So pause the video, take a moment, write down this chart, and then as we go through, we're going to slowly fill those in. The first particle we're going to talk about is the electron. Now, the electron, we found this using what we call cathode rays. And so J.J. Thomson is the first one to discover this back in 1897, right? So more than 200 years ago. Oh, sorry, not 200, more than 100, and I guess 30 years ago, we discovered this. So what we could do is streams of negatively charged particles were found to emit when we had what we call a cathode tube, right? And those rays caused this phosphorescence, right? We could see a response on the screen. Now, a cathode ray is basically, we had one side of that tube that was negative and we had one side that was positive, and we would flow some sort of electricity around it. We would excite it. When we put a fluorescent screen on that tube, we could then see these particles travel from one side to the other. And if we held a magnet, like they're showing in this picture, it would attract those particles towards its positive side. And so that's how we could figure out what charge those particles were. So at that time, we knew that there were these negative charged particles, and we could measure them. So one thing that he did was he measured the charge to the mass ratio. And so, sorry, this got reformatted. That should be 1.76 times 10 to the 8, what he calls coulombs per gram. So he could flow a significant amount of these particles, and we can measure the mass change, and we can figure out how much charge changed over time. So that was what we did back in 1897. From there, we kind of built upon it. Robert Millikan developed this oil drop experiment in 1909, and the idea was to then determine the mass of an electron. So we knew that there was this ratio between the charge and the mass, right? That's what we have found out in this experiment. And so what we wanted to do now was, instead of having just all of those particles go and measuring the overall charge, he tried to limit the electrons that were being released. And so he sprayed these oil droplets, and then he would use an electric field to kind of keep the negative ones away from the positive ones, and then use that piece of information to help figure out the mass of an electron. So electrons were kind of our first part that we discovered. At that time, we didn't know about those protons and those neutrons, right? And so, and don't worry, we're going to come back and we'll talk about our protons and our neutrons in just a second. And so Thomson, he proposed what he calls the plum pudding model of the atom. It was this idea that we knew that there were these negative charged particles, those electrons, but we knew that there was some positive amount in those atoms because those atoms seemed to be neutral. And so he thought that it was just like this, where we kind of embedded those electrons spread out evenly throughout the whole atom. And around them, they were kind of in this cloud of positive holding them in. And so it's called the plum pudding model because this is plum pudding over here on the right. And so when he described his model at a conference, people were like, oh, that sounds a lot like plum pudding. And that concept kind of stuck. So that was our plum pudding model. That was these negative charged particles embedded in all of this positive charge. Now from there, we started to explore this concept of radioactivity. And so this was first observed by Henry Becquerel, but the people that really pioneered our understanding of it are Marie and Pierre Curie. And so why this was important was this is how we really started to discover and understand more about these subatomic particles and their energies. So there's three kinds of particles that we kind of generally talk about. One are alpha particles, which are going to be positively charged. One are beta particles, which are going to be negatively charged. And the third one is going to be our gamma rays, which don't have a charge, but they have a lot of energy with them. So Rutherford kind of classified these three types of radiation. And so before we started to do it, our understanding of the atom was tied in here with Thomson's plum pudding model. So what Rutherford wanted to do was he wanted to do some experimentations with that model to either confirm Thomson's or present a new model. So what he did was he took those alpha particles. Now, if we remember about the alpha particles was that they were positively charged. They were also really small. And so different radioactive substances would spontaneously make these alpha particles. And so his goal was to direct those particles through a really thin gold foil and try to measure what would happen to them. Would they go directly through? Would they get deflected or around the screen? And he would kind of want us to wait and see. And so I want you to take a moment and think about it. What happens if we have something that's positive and it gets close to something that's negative? Do they interact? Are they attracted to each other? Do they collide with one another? What if that's a positive thing and another positive thing? Do they attract each other? Do they repel each other? And so looking at Thomson's model, if you were a ball of positive, a really small ball of positive, and you were coming through that atom, what do you think you would do? Would you go right on through? Would you be deflected? Now, the thing I like about Rutherford's experiment was not only was it pretty clever at that time, but it was also very thorough. So when he set this up and he set up his detection screen, he might have thought just to put it in this back half, that when those particles hit that gold foil, the chance that they got deflected so strongly was probably slim. And he would look for those particles to make it through onto the other side. Now, instead, he was a very thorough scientist. And so he made it almost all the way around. He just left a small gap where those particles would be introduced. So that way he could see them wherever they deflected in, like almost 360 degrees. He also paid attention to a lot of those smaller, to a lot of the kind of what we might consider outliers, but some of those not as often coincidences of what would happen. So when he shot those particles through, most of them went straight on through with very minimal or no change. But there were some, 1 in 20,000, that were deflected back at these really wide angles. Some bounced back and almost directly went back to their source, so where that came from. So this only shows up because he paid attention to those very rare responses in order to really understand what was going on. He also only was able to tell because he had set up such a thorough experiment to begin with. So when those alpha particles, those positive cluster of energy, when they hit the atom, what he discovered was that once in a while, if they hit right near the middle, they would ricochet around. And that's what happens when we have a positive thing and another positive thing. When those two get next to each other, they repel each other. And so then that positively charged alpha particle could get reflected away. All the other times, if it didn't get really close to that positive charge at the middle, then it would go right on through. And so this is the idea that the electrons, they must be pretty well dispersed throughout the atom. They didn't interfere with the positively charged protons or positively charged alpha particles we were sending. But at the very center, there must have been a really tight cluster of positive energy that was then repelling those alpha particles. And so he developed this model where we have a nucleus that contains our protons, and around them, containing most of the, or taking up most of the volume of the atom, is where we would find our electrons. So most of the atom is kind of this empty space, and there's just a little bit of positively charged stuck in the middle. Now, as food for thought, would you expect the number of alpha particle scatters at large angles to increase or decrease as we increase the gold foil? So if we put more and more foil there, would that increase or decrease? And so I think that they would increase. And the reason why is that as you shoot those gold foil particle, or as you shoot those alpha particles through, if we have gold foil, we're going to start to get several layers of those nuclei. Now, that means that that alpha particle has to go directly down through this pathway in order to avoid hitting anything, any of those nuclei. If it's a little bit off, then it will collide with one of those nuclei that's farther in the back and reflect. And so I think that the number of alpha particles scattered should increase because it's more likely that they're in collide with something. Now, because of this, we were then able to kind of develop this postulate about there being this positively charged proton, and that we think that they should all be in the center. And so over time, we started to then separate them out to try to isolate them. And so we eventually named that a proton. And so it's called a proton because it's very positive. The one that was harder to discover was what we call a neutron. Now, a neutron is really similar to a proton, but it doesn't have a charge. So when we look at our three particles, these are the three particles. We have electrons, protons, and neutrons. Now, electrons are very light. Their mass is 1/1836 that of a proton. They do have a negative charge. A proton, on the other hand, has a positive charge. It has a lot more mass, but its positive charge is equal to that of an electron, just in the opposite. So one proton and one electron, their charges will cancel out and they'll become neutral. A neutron is basically the same mass as a proton, but it's a neutral in its charge. And so as we go through this class, one of the things that you really want to remember is how these charges kind of interact with each other. Positive charges repel other positive charges. Negative charges repel other negative charges. But unlike charges, so a positive will attract a negative, and the negative will attract a positive. So this is where people say opposites attract, right? They kind of get that idea from magnets because the opposite charge, that positive, will attract the negative charge. Whereas when they're the same, they actually repel and they move away from each other. And so based on Rutherford's understanding of the atom, we then decided that we would put all of those protons and all of those neutrons, we're going to put them in the center of the atom. It's called the nucleus. And this is a smaller portion of volume, but it's significantly larger inside of its mass. So most of the atom is this empty space that our electrons take up. And those electrons, we call them that they form a cloud around the nucleus. So you don't want to say that electrons are not part of the atom. They are still part of the atom. They're just outside the nucleus for their location. So the volumes that the electrons take up are a lot higher than the protons and the neutrons, but the mass of the protons and the neutrons is a lot higher than that of the electron. The last part that we're going to talk about for our topic today is we're going to talk a little bit about our atomic numbers and our atomic masses. So our atomic number is defined as the number of protons in the nucleus of an atom. And why this is important is our atomic number is going to be how we determine our elements. So it really only ever comes down to how many protons are there inside of that atom, and we're going to use that to determine our elements. Now, overall, our atoms, when they're found, they're going to be neutral. And what that means is that their charge is going to be equal to each other. So our number of our protons should equal our number of electrons in order to keep that charge balanced. Now, if it doesn't, then we would have something called an ion. An ion means that it's an atom with charge. That means that it could be positively charged or it could be negatively charged, but it's because our protons and our electrons are not equal to each other. But for now, we're just going to deal with atoms that are neutral. Now, when we write them, all elements can be abbreviated with a symbol. So carbon can be rewritten as carbon with just a C. All of those elements will either have just one letter or two letter. And it's really important that you pay attention to uppercase and lowercase, because C and O and C and O are not equal to each other. This top one is a carbon and an oxygen. The bottom one with a large C and a lowercase o is just the element cobalt. So it's really important that you capitalize the correct ones and make the other ones lowercase. Don't just rely on their size to do that. You want to make sure that you're following the normal the normal methods of writing. So what that means is, even for our aluminum, don't write AL, just write A and L. So if you are used to writing your M's in a different format, or some of your other lowercase letters in a different format, you want to make sure that you fix that for this class, because we will go with standard handwriting, I guess. If you have questions about that, make sure you ask. So when we write down that of an atom of an element, we can use that symbol to start with. From there, all of those numbers that get written around that symbol matter. They tell us different things, and so their placement also matters. Anything that's written in that upper left is what we're going to call the mass number. And the mass number is basically the mass of that atom. And that's going to be in the units AMU, which stands for atomic mass unit. It can also be in the units grams per mole. as those two are the same. So the one that's before the C, but on the bottom side, is our atomic number. Now, a lot of times that atomic number doesn't get written because carbon is always defined as having the atomic number of 6. It's why when you look on the periodic table, that carbon will have that number associated with it. So the mass number is going to be that superscript before the symbol, and the atomic number is going to be that subscript before the symbol. Now, when we talked about our masses, we said that our neutrons and our protons are a lot bigger in their mass compared to that of an electron. One proton is just about 1 AMU. One neutron is just about 1 AMU. And an electron is so light that a lot of times we don't even worry about its mass because we would need 1,800 of them before we would finally be equal to 1 proton or 1 neutron. So a lot of times when we talk about the mass numbers, we're really just adding up the number of protons and neutrons in the nucleus of the atom because they are the only masses that really make an impact on that value. So isotopes are when we have that same element, but with different masses. So all 4 of these are example of isotopes. Some of these are naturally found and some of them can be synthesized, so man-made. But this is what happens when you can have a different ratio there. And we're going to think about why that is. Now, we know that their mass is different, but their number of protons are always going to be the same. Your number of protons, it will always tell you what element you're dealing with. If you change the number of protons, you're dealing with a new element. Neutrons are different. If you change your neutrons, you're just going to change their mass. And so how we make isotopes is we keep the number of protons the same, but we adjust the number of neutrons. So carbon 11, this one here, it has 6 protons, but only 5 neutrons. Carbon 12, which we more commonly see, has 6 protons and 6 neutrons. And so your mass number should always equal your number of protons plus your number of neutrons. And you can see that here. Carbon 14, we should have 6 protons. And if we have 8 neutrons, you can see where that 14 comes from. Our electrons, they're not tied in with our isotopes because they're not necessarily changing our mass so much, but they're tied in with our charges. So our electrons, when we change our number of electrons, that's how we're going to get into our charge. But we'll talk about that a little bit later when we get into ions. But I like to include that just so you get an idea. You've heard it before. Now, the atomic mass is this AMU. And so atoms have extremely small masses because they're very tiny. The heaviest known atoms are only about 4 times 10 to the minus 22 grams, so really small. And so we use this AMU to kind of keep things a little bit easier as we talk about them. It makes it a little bit easier when we talk about atomic masses, right? But it doesn't quite equal a gram. And so you want to make sure that you understand that an AMU is much, much smaller than a gram. Now, because in the real world we use like large amounts of atoms and molecules, a lot of times what we do is we use the average masses in our calculations. Now, an average mass is found by taking into account all of the isotopes of an element, and we take their relative abundance. So we do the atomic weight or atomic mass as being their weighted average of all of their naturally occurring isotopes. The idea behind it is that when we are doing our experiments, we're kind of like reaching in there and we're grabbing a whole bunch of carbon, or we're grabbing a whole bunch of atoms of hydrogen. Some of those hydrogens might be H1. Some of them might be hydrogen 2 with an extra proton or with an extra neutron there. We don't really know. So we're just going to take on average what they will be and hope that overall we're just getting an average sample of it. Now, there are times where we might find just one specific isotope and use just that. So we might just use exactly carbon 12. And so then our mass would be that 12. But a lot of times what we're doing is we're using just an average carbon, and so we need to take that average. So when it's saying that we multiply them by their relative abundances, what that means is that we have to look at how often they show up. And the reason why this matters is that our technology has actually gotten good enough that we can start to separate away one isotope of the element from the other. So this is an example of what we call a mass spectrometer. And when we send these particles down this mass spectrometer, it can use its charge. So it's using magnets here to help separate them apart. And we can see how often this chlorine with a 37 atomic mass comes through, and this chlorine of a 35 atomic mass comes through. And so this is one way that we kind of have been able to find their relative abundances, and that's how we make those atomic masses or atomic weights. Now, atomic mass and atomic weight gets used pretty interchangeably, and that's just because our mass is a little bit better of a term. It's about the amount of material. Our weight has to deal with the pull of gravity. But if all we're doing is talking about them and we're all doing it in the same gravity pull, then our weight and our mass can be used fairly interchangeably, right? It's only a bigger problem when we start moving on to like different altitudes, or if we start to move to going into outer space to do some chemistry there. But for now, we can do either one. And since sometimes 37 chlorine shows up a lot less than chlorine 35, when we talk about our average atomic mass, we're trying to account for that. And so that's why we're using that weighted average. So we're going to practice this one here. We're going to take a look at those chlorines. Now, 75.77% of that chlorine showed up as chlorine 35. And it's got an atomic mass of 34.97 AMU. On the other hand, our chlorine 37, it was a smaller peak. And so about 24.23% showed up as that. And so total, you can see that adds up to 100%, which is all of our chlorine that's going to naturally occur. And so it's either showing up as 35 or it's showing up as 37. And so when we're trying to find their atomic mass, what we want to do is we want to scale them based on how often the percentages. So 36.97 is the atomic mass of our chlorine 37. We're going to change that 24.23% into a decimal, and we're going to get this 8.9578 AMU. That's the fraction of that mass that shows up as chlorine 37. We do the same thing with chlorine 35. We just use its mass and its fraction. We get a much larger number, 26.4968. And so on average, when we add those two values together, on an average, chlorine should have a mass of 35.45 AMU. That doesn't mean that the chlorine atom itself actually has a mass of 35.45 AMU, but it means that as a collection, we would have that value on average. So if we want to take that and multiply that by 10 atoms, we would have 354.5 AMU roughly of material. And so that's why we're using the average value, is because we're dealing with so many atoms as we go through it. So that's all the material we're going to cover today. what I would like you to think about is we're going to do some practice problems and work through those atomic masses a little bit. And then we're going to do some practice problems and practice identifying our protons, our electrons, and our neutrons. So in this case, two isotopes of boron are found in nature, boron 10 and boron 11. Let's look on our periodic table and determine which isotope is more abundant, boron 10 or boron 11. So pause your video and go and take an attempt at it. What we should notice is that boron 11 is a little bit closer to the average weight that's drawn on the that's written on the periodic table compared to that of boron 10. That means that our boron 11 must be a little bit more abundant. If they were perfectly equal, we would have 10.01 times 50% plus 11.01 times 50%. And we would get a value that was almost right there in the middle of them. We should get something like 10.51. But because we are higher than 10.51, that means that this number must be a little bit higher. Might be something like 0.75. And this one would have to be a little bit lower. And so as this value continues to go up, so does our average. I get closer and closer to 11.01. If this number was to keep going up, then our mass would instead go down and we'd be getting closer and closer to 10.01. So it just depends on which direction we're going. And so that's how we're able to tell which one is more naturally occurring. I want you to go ahead and calculate the average atomic weight for magnesium using these values. And report that one out to 4 significant figures for your value. We should have gotten 24.31. So you want to practice with those, make sure you understand how you find your weighted averages. And then the last thing that we have is let's go ahead and use these symbols and start to think about how many protons, neutrons, and electrons there would be. So as an example, I'll do the first one, carbon 12. So carbon, I look on the periodic table, it's got an atomic number of 6, which means it has 6 protons. I can take that 12 minus my 6 protons, so that means I have 6 neutrons. And because there's no charge on them, then I know that my electrons must be the same, 6. So you can do that. You can go through your next two. These ones down here, those are us starting to introduce ions to you. And so you want to think about how that changes things. In this case, this one's a positive one. So if you're a positive ion, do we have more protons or do we have more electrons? Protons are a positive one, so this means that we have more protons than we have electrons. Bromine is a negative, and so that means we have more electrons than we have protons. Now, as we look at aluminum, aluminum always has 13 protons. So it doesn't matter that it's the positive ion of aluminum, it means that we're still going to have 13 protons. If we had 14, we wouldn't be aluminum anymore, we would now be silicon. If we had 16, we would be sulfur. So we can't change the number of protons. That means that our neutron count should be 14, because that's how many would give us this mass weight of 27. But our electrons can change. So if we need a +3 charge, that means that we should have 3 more protons than we have electrons. And so that's why we can only have we can only have 10 electrons. And that's how we can do kind of piece those together. Go ahead and pause the video, do your other ones, and then you can compare. And there's our last one. All right, good luck.